Okay, so now we'll move on to the next few problems, which is 35, 36, and 40. And the instructions for that are find the bounds to the zeros of each polynomial function. Obtain a complete graph of f. And to do this, you have to use the bounds on zeros theorem, which appears on page 246 in your textbook. But rather than going through the theorem, which is perhaps a little complicated to just explain as is, I'm just going to race and jump right into the problems, and hopefully you can learn how to use it from there. So problem 35 is right here. One important thing about the bounds on zeros theorem is that if you have to, the leading coefficient has to be 1. So if you end up with a situation like this where the leading coefficient is something other than 1, you're going to have to factor that out first to get the leading coefficient to be 1. So we factor out the 2, and that leaves us with this, which is x to the third plus 1/2 x squared minus 1/2. So that's the term you work with. You have to calculate basically two maximums, or equations involving two maximums, and you end up with two numbers, and then you take the smaller of those two numbers, and that sort of defines the bounds that you're looking for. So the coefficients that you use to calculate that are the very last coefficient, which is going to be the constant value, and all the coefficients up to the one right before the first one. So you don't use in this case, you don't use the very first one, which is x to the third, but you use all of the other coefficients, 1/2 and 1/2 and all the way up, except you don't use the first one. Actually, the coefficient of that one is 1, but we're not going to use that. Okay, so the first maximum we have to calculate is the maximum between 1 and all of the coefficients added together, except for the very first one, which we're not counting. So we take the 1/2 here, we add that to the 1/2 here, so that's 1/2 plus 1/2, and we get 1 there. So we have to determine the maximum between 1, and obviously that's just 1. So one of the maximums we're looking for is the 1 right here. The next maximum equation we have to deal with is 1 plus the maximum between all of the coefficients we're considering. So we're considering this 1/2 and this 1/2, and the maximum between 1/2 and 1/2 is just 1/2. So we have to take 1 plus 1/2, and that's going to give us 3/2. So that's the other maximum value we're calculating. So we take the smaller of those two values here, and in that case the smaller value is going to be 1. So take the smaller of the two numbers, 1 and 3/2, and you take the smaller one, which is 1, and that tells you that the bound of zeros lies between -1 and 1. So using that bound, we'll go ahead and plot it, and I plotted out the function, which is the original function f of x. I went ahead and plotted that out using the bound that we just determined to be from -1 to +1. And we see that, let me make that smaller so you can see it. So we go from -1 to 1, and we see that our function fits really nicely, and any zeros that this function would have, according to the theorem, would have to lie between -1 and 1. So this provides a good basis for knowing what the bounds on your x-axis are going to be when you graph the function. So anyway, that's how this turns out. It turns out that this function has a 0 right here. We don't have to calculate it in this particular set of problems, but anyway, it's gonna lie right here. It's gonna be, I guess, I don't know, somewhere between 0.5 and 1. But that's how the graph is, and this is the bound that we calculated from -1 to 1. Okay, so now we'll move on to the next one, and that is f of x is 3x to the third minus 2x squared plus x plus 4. Again, the leading coefficient has to be 1 for calculating the maximums that we're going to be calculating, so we factor out the 3, and that leaves us with x to the cube minus 2/3 x squared plus 1/3 x plus 4/3. in order to calculate the maximums, we're going to be using all of the coefficients except for the very first one. So we're going to be using the constant term here, the 4/3. We're going to be using the one associated with x, which is 1/3, and the one associated with x squared, which is 2/3. And we're not going to worry about the 1, right, or the coefficient 1 that's associated with the x to the cube term. So the first maximum value we have to calculate or determine is the maximum between 1 and all of the coefficients we're considering added together. And that turns out to be, let me see, 4 plus 1 is 5, plus 2 is 7. So it's the maximum term between 1 and 7/3. And in that case, 7/3 is greater than 1. So the first term we're going to consider is 7/3. The second maximum we have to calculate is 1 plus the maximum between all the coefficients we're considering. And in that case, the largest one looks like it's going to be 4/3. So 1 plus 4/3 is also 7/3. So our other term is going to be 7/3 too. We take the smaller value if we had one. Here they're both equal, so we can take either one. So we'll take 7/3, and our bound will lie between negative 7/3 and positive 7/3. So we plot this function, our original function here, and we plot that using the bounds negative 7/3 to positive 7/3 for the bounds on our x-axis. And when we do that, we get something that looks like this. Again, it fits really nicely. And we see that the 0 is about here, but we we don't have to calculate. It's something somewhat greater than -1 and not quite up to negative 0.5 yet. All right, so I guess the last one in this problem set is 40. And that one, they give us the function 4x to the fourth minus 12x to the third plus 27x to the squared minus 54x plus 81. And again, our leading coefficient has to be 1 to do these calculations. So we factor out the 4, and that leaves us with the equation here, which is x to the fourth minus 3x to the third plus 27 over 4 to the x squared times x squared minus 27 over 2 times x plus 81 over 4. So we've got a lot of terms to consider. We consider all of these coefficients, this one, this one, this one, and this one, except for the leading coefficient. We don't consider that. So the first maximum we have to calculate is the maximum between 1 and the sum of all of the coefficients we have under consideration. So we're going to consider this one 81 over 4, 27 over 2, 27 over 4, and the 3 here. Oh, and when we add these together, we're adding together the absolute values of the term. So whether it's negative or positive doesn't really matter. So we just add these all together. And I went ahead and calculated this out. As it turns out, the maximum between these is going to be whatever these are all added together, and that's 87 over 2. And obviously 87 over 2 is a lot bigger than 1. So 87 over 2 is going to be our answer here. The next maximum value we're going to have to calculate is 1 plus the maximum of all the coefficients under consideration. And among these, it looks like 81 over 4 is the largest one. And so we take that and we add that to 1, which is going to be 4 over 4. So it's 4 over 4 plus 81 over 4, which is going to be 85 over 4. So we have to take the smaller value between 87 over 2 and 85 over 4. And as it turns out, 85 over 4 is smaller than 87 over 2. So we take that one, 85 over 4. So our bound should lie between minus 85 over 4 and positive 85 over 4. So I plotted it using those as my boundaries. And it turned out to look something like this. Now actually in this particular equation we don't have any zeros. It's all way above the x-axis. But the bound is still helpful in graphing it in the initial place. So we go ahead and put this in. In this case actually the concept of bounds on zeros isn't so essential because we really don't have any zeros for this function or for this graph, but nevertheless, when we calculate the bounds between what was it, negative 85 over 4 and positive 85 over 4, That's more or less how it's going to graph out. And if you do it on your calculator, I guess you can use that to define your x min and x max that you're going to be using on your own calculator. And then you might still have to adjust the vertical axis to have it fit nicely. In my case, I have it going from, I think, from 0 to 1000, but you can adjust that one once you get the X one adjusted. At least it will enable you to see where the zeros are going to be if there are any zeros. Okay, so basically that's that set of problems, and then we'll move on to the next one a little later.